So the next topic here is orthogonal rotation of axis. So what is orthogonal rotation of axis? We studied some two system earlier, the K system and the K dash system. So I am merging these two system. Now here we have a K system and the K dash system is just like that. If I move this system, so this system coincide with the K system, like K dash system coincide with the K system. So that means this is basically called the rotation of the axis. Now further is I have this table and this is known as the transformation matrix, and it is written as like T that is equals to Lij. Lij is basically we studied its definition earlier. So that is Lij, that is in matrix form. I can write it as L11, L21, L31, L12, L22, L32, L13, L23 and L33. Now I am taking the transpose of this matrix. So while taking the transpose, the rows change into column. So L11, L12 and L13, this first row become the first column. So I took the transformation of transpose of this matrix. So T dash is this matrix. Now taking the product of T with T dash like this. Now here I am multiplying these rows, and if you can see here T and T dash Ij, that means if I write this matrix in the form of this equation, as you can see here in the first column, the first you can say the first index are changing and the second one is fixed. So that means I can write it as Li1, and the other one is, now this is the column and I am taking the row of this this matrix. So the row here, as you can see here also the first index are changing but the second one are fixed. So in place of this I can write it as Lj1. Now next column, so in next column I can write it as Li2, and in place of this row I can place that Lj2. Now further is Li3 and Lj3. So combinedly I can write it as Lik and Ljk. Now using the definition of this one, so Lik is basically equals to Ei dash dot Ek dash, and Ljk is basically equals to Ej dash dot Ek. Now simply if I can interchange the dot product here, so I can write it as Ek dot Ej dash. There is no you can say I can easily write it if I have dot product in between these two unit vectors. So I can write it as, so here is K and here is also K. So I have, according to some result, I can write it as that Ei dash dot Ej dash. The dot product of this vector is basically, according to this result, is equals to this. So that means Ei dash dot Ej dash, and we studied a result earlier that this is equals to del of Ij. We studied previously that Ei dot product with Ej is equals to del Ij, but similarly this case also hold for Ei dash dot Ej dash. This is also equals to Kronecker delta, and this Kronecker delta, if I write it in matrix form, this is equals to I identity matrix. So this is basically the orthogonal rotation of the axis. Orthogonal mean every unit vector or the every axis has the angle 90 degree right angle between these two matrices. That means we have the angle between these axes are 90 degree. So next here is some concept about the right-handed orthogonal you can say transformation and the left-handed orthogonal transformation. So basically if I take the determinant of the matrix T and T dash, so that is equals to, you can say, plus minus 1. So if I have the determinant of you can say of T is plus 1, that means the determinant of T is 1, simply positive 1, then this transformation is known as right-handed orthogonal transformation, and if determinant of t is -1, then this transformation is known as left-handed. So here is some t is basically equals to identity, or determinant of t is 1. Now further here, in the previous section, we are opening this, you can say, equation 1. So this is del ij. So if I multiplied this L11 with L1, if I multiply this these two matrices, so I got this result. This is basically the product of t with t dash, and t with t dash product is equals to identity matrix like this. And comparing these two matrices, so I got that result, that L11 square plus L12 square plus L13 square is equals to 1, and this result is equals to 0. Also this result is equals to 0, and this result is also equals to 0, but this result is equals to 1. This is also 0, this is also 0, this is also 0, and this result is equals to 1, like this. They write it here. So next is we have some question related to the transformation. We have to check whether the transformation is orthogonal and right-handed. Orthogonal mean we have to check whether the product of t with t dash is equals to identity matrix. If that is equals to identity matrix, then that means this transformation is orthogonal. But and further, if I take the determinant of that t, so if the determinant is positive 1, then it is right-handed, but if the determinant is negative 1, then it is left-handed. So first we have to check this. I am taking this transformation and I am going to check whether it is orthogonal or not. So I am taking the transpose of t. So transpose, in transpose I change rows into column. So the first row change into first column like this, and the second row change into second column, and the third row change into third column. Now the product of this, taking the product, if I multiply these two matrices, so I got this result, this identity matrix. So that means this t is orthogonal. But in some cases, if we don't have identity matrix, there is some another journal matrix, then that means this t is not orthogonal. So here I have identity matrix, that means this transformation is orthogonal. Now in the next step, we have to check whether it is right-handed or not. So I am taking the determinant of this t matrix. So while taking the determinant, that result is equals to 1. That means this t is basically orthogonal and right-handed. Now in the next question, we have another t, and we have to check whether it is orthogonal but left-handed. So first we are taking the transpose of t. So here is the transpose of t. Now further multiplying t with t dash. So that result is identity matrix. So that means this t is basically orthogonal. Now in further step, I am taking the determinant of t. So while taking the determinant, the result is equals to -1. So the result is -1. That means the transformation is orthogonal, but that is left-handed. So this is the basic concept of orthogonal and how to check the transformation is orthogonal, and the matrix, or sorry, the transformation is also left-handed or right-handed. So there are some proper and improper transformation. So the proper transformation is those in which determinant of t is 1. In generally we can call it right-handed, and if the determinant is -1, then this transformation is known as improper transformation. Now further we have some cases here, that the transformation for which t is identity, the unit matrix, this is called the identity transformation. Now here is some, you can say, the proper transformation can be obtained from identity transformation by continuously rotating the axis, and the improper transformation can be obtained from the identity transformation by two types of discontinuous or discrete operation. Now here these two operations are basically for the improper transformation, the reflection and the inversion. So here we have reflection. In this is operation in which the new coordinate system O x1 dash, x2 dash and x3 dash obtained from the original system, you can say, by inverting or reversing the direction of one of the axis of of the later, and the other two remaining in their original position as shown in the figure. So as you can see here, this is basically x1, this is x2, and this is x3, and I place another coordinate system o x1 dash, x2 dash, x3 dash on the previously you can say coordinate system, but here the one direction or the one axis is in opposite direction. Like here is x1 is in opposite direction of x1 dash, but all other are in same direction of x, like x2 and x2 dash in same direction, x3 dash and x3 is in same direction, but x1 and x2 dash are in opposite direction. And in next figure, here x2 is opposite direction, and in this figure x3 is in opposite direction. So in this case the transformation will be, that means that x1 dash is equals to minus x1 because the direction is changing here. All other you can say all other axes are same. And in second figure I can say that x2 dash is basically equals to minus x2, and all other you can say axes are same. Now in the third, here is x3 dash is equals to minus x3 dash. So this is the reflection, this is called the reflection here. Now further is we have some, I can say that now here we have some, you can see the corresponding transformation matrix T will be this one. If I write these equations in the form of the matrices, so in place of this I can write minus 1, and this is 0, and this is also 0, and in place of this I can write 0 and minus 1, 0 and 0, 0 and minus 1. So like this I can write it as like this. These are the positive, or I can say that these are the transformation matrix T according to all these equation. So I can write it as like this. Note that from each of these matrix determinant of T is minus 1, because these are basically improper transformation. So that means improper transformation we have always the determinant of T is minus 1. So I can write these equation in the form of matrices like this, this and this. Now further is inversion. Inversion is basically, this is an operation in which the new coordinate system ox1 dash, x2 dash, x3 dash is obtained from the original system by inverting the direction of all the coordinate axes. In the previous section we just convert, or we just reflect the invert the direction of only a single axis, but here we are inverting the direction of all the axes. So that means x1 dash is equals to minus x1, x2 dash is equals to minus x2, and x3 dash is equals to minus xe. So if I write these all three in matrices form, so I can write it like this. In this matrix, as you can see in the reflection, I have only that single matrix x1 is changing here, and in this matrix only x2 is changing here, and in this matrix only x3 is changing here. All other matrices are same, all other axes are same, but here in inversion we are changing all the axes. So that means I can write the transformation like this. And if I take the determinant of this, so this is also equals to minus 1, because these are the operations of the improper transformation.